Lab 4, Faraday's Law. Purpose. In this lab, we collect observational data of a magnet falling through aluminum foil. 2, we model the magnet/tube interaction computationally. And 3, we compare the computational predictions with observed data, all to predict the properties of Faraday's Law through a magnet bar and aluminum foil. System and surroundings. The system is the magnet bar, and the surrounding is the tinfoil and everything else. In the picture, you can see the tinfoil that I use and the magnet bar that I use. If you look closely, the magnet bar has tape on the north axis. Data collection. In the left image, you can see me dropping a magnet bar through the aluminum foil, and on the right side is how I calculate the data. The first number in the first column is the frame that the magnet enters the tube. The second number is the frame the magnet exits the loop, and the third column is the elapsed time. As you can see, the average was equal to 0.364 seconds. I also measured that the length of the aluminum foil was 30.5 centimeters long and 1 centimeter in thickness. Here's my code. In the top left, you can see the aluminum foil setup. In the top right, you can see the magnet setup. MU mag was equal to 80, which I calculated for my Lab 2 experiment. In the bottom, you can see my dipole function. The dipole function was calculated via the formula sheet. In the top, you can see my flux function. The flux function was calculated via the Lecture 43 video. And on the bottom, you can see my calculations for both B field and magnetic force. And here I use Physics 1's update formulas to update the position of the bar and the velocity of the magnet bar. Here is the resulting code. The time in the tube was approximately 0.225 seconds. The result was really close to what it was in real life, off by zero point 0.1 seconds. The error could be a result of camera frame rate, as the magnet bar falling through the tube was too fast for the camera to be captured accurately. What if? What if the resistance of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? In the normal case, a magnet would induce currents in the conductor, reducing the motion of the magnet down. In the case that resistivity is equal to zero, the current generated would perfectly oppose the magnet's motion, meaning the magnet would not fall and would instead levitate in the tube. What if? What if holes or slots were cut into the tube? How would this affect the ring's currents in your model? Without slots, the currents within the tubes are closed, generating opposing magnetic field to slow the fall of the magnet. With holes, the current within the path is broken. Current no longer circulate freely within the tube, therefore slowing down the effect is reduced. With, with holes, with holes, the current within the path is broken. Current no longer circulates freely within the tube, therefore the slowing effect is reduced on the magnet.